In this work, we present a novel approach to solve PDE-constrained inverse problem using graph neural network and generative priors. PDE-constrained inverse problems aim to infer knowledge from observation data by leveraging simulation and mathematical models. Given sparse measurements and the underlying PDEs, we want to extract unknown physics parameters. Such problem appears in many application domains across science and engineering. In general, we solve those problems via optimization. Given current estimated parameters, a simulator is used to generate predicted dynamics. It is then compared with the sparse measurements, and the goal is to minimize the difference between two. To solve this optimization problem efficiently, we need a fast solver. Over the course of optimization, we need to do full forward simulation many times, and this can be very time-consuming. Besides, since we only have sparse observations, the problem is highly ill-posed. Therefore, we want to have prior or regularization in order to avoid bad local optima. To address those two problems, we propose to use a GN-based simulator for fast-forward modeling and a learned generative prior to model the dataset distribution. The GN-based simulator takes the current state on a mesh as input and predicts the state at the next time step. Such GN-based simulator is fast and allows us to learn over larger time steps and on much coarse meshes, where classical solver would fail. Here, we show an example ground truth simulation on a fine mesh and the GN simulation result on the coarse mesh. We see that they match closely with each other. Here, we also compare the GN-based simulator with popular CN-based methods. GN operates on irregular meshes with adaptive resolution, which is a more efficient representation. We also empirically show that GN has better long-term accuracy compared to CN-based methods. Therefore, we use a GN-based learned simulator for speed, accuracy, and scalability. For the prior network, we use a generative model to learn the dataset distribution. We constrain the solution space to the manifold learned by the prior and thus avoid bad local optima lying far outside the dataset distribution. We use a coordinate network as our generative prior. For each field distribution, it has a corresponding latent code Z. The prior network maps a point X and this latent code Z to the field value at that point. In this way, we can query field value at any point in space, hence make the prior network mesh independent. Okay, now let's look at the whole pipeline for solving a classes of inverse problem. We take this wave equation as example. From sparse observations and PDEs, we want to infer the initial states. We first pre-train our GN-based solver and learn prior using a dataset generated using classical solver. At test time, given current estimated latent code, we use learn prior to decode it to physics parameters. Decoded parameters then pass to the GN for forward modeling to obtain predicted dynamics. Latent code Z is then optimized to minimize the difference between observation and predicted dynamics. Here, we present some of the results. Given sparse observations in space and time, as shown at the top left figure, we want to infer the initial state of the system. First, we observe that with proposed learn prior, we get significantly better results. We also observe that the GN-based approach outperforms CN-based method at both coarse and fine resolution. GN yields better results compared to classical simulator simulated on coarse meshes. While GN is slightly less accurate than classical solver at fine resolution, it is 8 times faster, yield a favorable trade-off between speed and accuracy. We also test our approach on flow assimilation problem where we want to infer the flow field everywhere from sparse observations. Here, we show the result for different simulator with proposed learn prior. Again, we observe that the GN outperform other learning-based approach. GN is slightly less accurate than classical solver, but is 90 times faster. To summary, we developed a new physics-based graph neural network incorporating generative model for solving physics-constrained inverse problem faster and more accurate. Some limitation of current approach or future research direction includes leveraging gradient checkpoint to address the memory requirement during the enrolling. Generalizing learned physics solver across problem setting is also a promising research direction for future work. Thanks for listening and check out our paper and project page for more. Thank you.